For our next example, we have the series of pi over 6 to the nth power. So look at your formula sheet, and where you have some value to an nth power or something like that, actually n minus 1 is a geometric series. So kind of the big picture here is when you have a constant to some power of n, then it's probably geometric. So there's different forms actually, the geometric series, but the one that you have on your formula sheet is of this form. And so this just involves taking a little bit of algebra to realize all the parts. So first of all, notice that I can write this pi to the 6n is n minus 1 plus 1, which is kind of silly because that's n, but I'm just showing that to show you that, hey, it's legit to write this as pi over 6 to the n minus 1 times pi over 6 to the 1, because that's a plus 1 part with our exponent properties. And now it's perfectly in the form of a geometric series, with our a is equal to pi over 6, and our r is where we test for convergence and divergence with geometric series is pi over 6. So again, looking at the formula sheet, you take the absolute value of r, just to be technically correct, and if it's less than 1, it's convergent. If it's greater or equal to 1, it's divergent. So thinking about that pi is approximately 3.14, then 3.14 divided by 6 is certainly going to be less than 1. So from there, we can determine that this is a convergent series. And we're done. So I wrote it up here, but just to be clear, you know, this is geometric. Absolute value of r is equal to pi over 6, which is less than 1. So we're going to move on to the next one. That was the short one. What I have is the series of n squared minus 1, or just kidding, minus n over n to the 5th plus n. So here we have a series which, if I took the limit of the a sub n, it would go to 0. So I can't use the divergence test. This may be something to just run through. It's kind of p-series-ish because it's n to some power, but when you have those multiple terms in the numerator denominator, it's not purely a p-series. So this lends itself to one of the comparison tests. And then there's maybe a small debate about which one. So usually a limit comparison test works more often than the comparison test, or direct comparison test. So I'm just going to go ahead and try limit comparison. The caveat with that is you have to be pretty good at algebra to use limit comparison, and it is longer. So, you know, there's trade-offs here. Anyway, regardless of the comparison test, we need to identify a b sub n. So our a sub n is n squared minus n over n to the 5th plus n. That's just what we got there. And then we're supposed to find some b sub n from that. So a little game to play is, in the denominator, notice that the n to the 5th is going to dominate as n goes to infinity, and n squared is going to dominate in the numerator. So a nice, cute, simple b sub n, for which we could determine very easily the convergence or divergence of its infinite series, would be the dominant terms in this case. If you have factors, aka multiplication, then you gotta play a little bit. It's the same game, but you kind of can't just ignore a factor of n, for example. So that reduces just down to n, or just kidding, 1 over n cubed. And when we have the sum of 1 over n cubed, what we have there is a p-series, for which we can use the p-test on the formula sheet. where p in this case is 3, and since 3 is greater than 1, we have a convergent series here. So whether you determine that in the beginning or not at this stage is sort of optional, but the point is I picked a b sub n for which I easily can tell the convergence or divergence. Otherwise it's not a good choice of b sub n. So I'm going to try limit comparison, which means I'm taking the limit as n goes as infinity of my a sub n over b sub n. You can flip them and it doesn't matter, turns out. So what I'll have is n squared minus n over n to the 5th plus n divided by 1 over n to the 3rd. Next thing is you want to multiply by the reciprocal of the denominator. So we have n squared minus n over n to the 5th plus n times n cubed over 1. So I'm going to simplify that a little bit by distributing my n to the 3rd on the top, and I'll have n to the 5th minus n to the 4th over n to the 5th plus n. So infinity over infinity, L'Hopital will take a couple of, quite a few iterations. There's some shortcuts here, but to be totally legit, I'm going to multiply by 1 over n to the 5th, which is the largest power in the denominator. So then what I'll have is n to the 5th over n to the 5th minus n to the 4th over n to the 5th, distributing on top. Down low, I'm going to have n to the 5th divided by n to the 5th plus n over n to the 5th. So I have the limit as n goes to infinity of 1 minus 1 over n, all that over 1 plus 1 over n to the 4th. So these guys are going to 0, which means my limit is 1. So, looking at the formula sheet for the limit comparison test, because this L is greater than 0, a little confusing because that's in the convergent and divergent column, but then look at the second part that's shown there and notice that your conclusion based on the convergence or divergence of b sub n. So we already did that above, but for our b sub n, we found that it was convergent, which means our series is convergent. And I use limit comparison. Okay, and that's it for that one.